That's what is called biorecognition, is this binding event to recognize what you want to detect, okay? And then you provide a stimulation. A stimulation is to see what changes you can detect by this binding. And optical, this stimulation is light. Light going through there and looking at its binding has changed the fluorescence of a probe that is binding or lifetime, right? Or you can have electronic sensor where it can send of like field effect transistors, some kind of electronic signal changes. Or you can have magnetic detection where magnetic response is changing. Or you can have electrochemical sensors where electrochemical activity is changed. So there are all these changes that can occur, and then you want to, that signature change, you want to convert that into signal that you can read. And what is the most common signal? It's an electrical signal you read. So transduction takes, in case of optical sensor, the optical change response converts into electrical, and then you record it, right? And now the whole game is that all these things, can we make it compatible with cell phone? Okay, so you have apps that can take all this signal and electrical input in there and analyze. Okay, by the way, you know that your cell phone also have optical signals. How do you take color image? Photograph with your cell phone. You have a light coming out, and reflected light can be color coded, spectrum analyzed, and then you have color image, right? So you can also use, now what we are trying to do is develop this sensing utilizing cell phone as a light source, as a detection, and then the advantage is that the signal can be encoded digitally, right? And through Wi-Fi you can transmit it to someplace else, right? So you can use cyberspace, diagnostics, right? And then telemedicine. So it can go to doctor office and can look at all these things that you have generated and prescribes from there the thing, and it comes in your cell phone, right? So isn't that an intriguing idea? It's not there yet. Telemedicine is not there yet, but that's something that one can do. So anyway, going back to this thing. So biorecognition principle is very often antigens. These are small proteins that are expressed on the cell surface of disease cell. And that is what is called biomarkers. Biomarkers are these antigens, okay, or something. Like earlier I showed to you Ramonomics, lipids. High concentration lipid is a biomarker, concentration lipid. But generally in these mechanisms, you look at antigens. These are small proteins that are overexpressed on the surface of their higher concentration on the surface. And these are called biomarkers. You want to recognize them. And one of the things is the antibodies. Antibodies are the proteins that your body makes to defend against these diseases. So you take these antibodies and put it in the surface of nanoparticles through conjugation. We'll talk about that later, the chemistry, surface chemistry. And then, so you're looking for this antigen through these antibodies, and they have a special affinity for certain antigens. So you can buy these antibodies from one of these companies, biochemical companies. They will make antibody that will be specific to certain kind of antigen, a disease signature you're looking for, okay? So how does it work? Generally these antibodies have these kinds of gaps, space, that exactly fits into the physical shape of the antigen. It's called lock and key. So you can say that this is sort of a lock, and this is the key. Antigen fits in there. Physically, there is no chemical interaction in here. Okay? So that's what determines the specificity. These holes are very specific to certain shape antigens. Okay, it's a shape matching. Okay, and you detect that. So maybe when it binds, either you label the antigen with fluorescent probe, then this whole, or antibody has a fluorescent probe, and you can, when there is combination, this thing, it lights up, you can see. Okay, so that's what you do. But light, again, is not, what changes are you taking? When we said you're looking at biorecognition over here, what events you can look for. So you can look for, in case of light, many things. Light has very important 3 different components. One of them is the wavelength of light that determines its color, what's coming out. So your label, you can just look at color of emission, right, coming out. The other one is, so that one is the wavelength, and that can shift by binding. Okay. The other one is change in intensity or absorption characteristic, like we talked about, in oximeter, absorption changes as it binds. Okay, or attenuation, the intensity changes. Okay, you can do that. The other one is phase change. The light also has a described phase propagation. Okay, remember? So phase is in 2 ways. Either you can polarize the light, and then you can look at the polarization, or in its propagation characteristic that you can monitor by interference. When you interference, you can see if there is a change of phase. Okay, so your sensors can take advantage of all these 3. Okay, and then frequency change can give you either in fluorescence or Raman or nonlinear optical effects. The geometries that we use in optical sensors can be optical fibers, light propagating through the fiber. It could be planar waveguide where you trap light into a plane, or you can trap light into thin film of metal and propagate as a surface plasmon. Lastly, also use microarrays so that you can have spatially resolved different pixels reporting different events. And when we use nanotechnology, we can use dye-doped nanoparticles in fluorescence sensors or quantum dots, or another concept called molecular beacon. We will talk about it. The other one is plasmonic sensors, where you use metallic nanostructures simply by color change. So this is another sensor, fluorescence change or change in Raman scattering. Okay. Then you can have microcavity sensors. One is photonic crystal and microspheres. So these are other methods of sensing. What we may have to determine is, based on your interest, whether we can just talk a few of these and skip this part because this is a lot of physics, or we can go through this because of your curiosity. You will all have to determine whether we want to spend time on this or not. I definitely want to cover these, and I want to cover a little bit of this. Huh? Yeah, this is more relevant to you, and this may also be plasmonics, but these microcavity things, we'll see. Huh? How many of you would like to have this covered? How many of you Let's just skip it. Either way, there is no opinion. Come on. Huh? All right. We'll decide when we come to that. So let's look at one approach, which is very interesting, and you can design that also opportunity for chemists and biologists. And this is what we call molecular beacon approach for sensing. And molecular beacon is designed. We do it tomorrow. Yeah, okay. So, yeah, you don't want your mind to be overloaded, right? Because and it gets oversaturated, as you said rightfully, you may not benefit. So let's, yeah, so we'll do it tomorrow. And so let's take a few minutes to conclude. Any question, comments, anything you want to learn? Yeah. Yeah, we'll do that then when we are talking about. We'll come back to those designs. So here, we are doing this fiber sensor, plasmon sensor, and we are doing the more plasmon arrays, and we photonic crystal, grating, silicon. Here is microsphere. Okay. So, yeah, if you're interested, we'll just talk about it 1 minute. Okay. We will start with see, the reason I want to where was it? All right, let me just say that many of you are into nanomedicine and nano, right? And we already have spent 2, and we are still not in nano fully. So that's why I want to rush through the first part so that we get into real nanomedicine. Okay, and I want to save at least 2.5 lectures on that. All right, so maybe half of the lecture tomorrow. We'll try to finish things and then get into nano. Okay. Somebody had a question here? No? Saturated.
Explain so well that we are no way.
Yeah. Well, I hope that in the course you're not just learning. You're also imagining things beyond, like where you could use. So he's kind of, there's some thought in you, hey, maybe I could do this way, you know. And I find that everything, I don't know everything. And I still consider myself as a student. And I learn from my own students. I'm talking to them and they ask some questions which in their mind may be questions that they don't know answer to, but in my mind I don't have an answer either, and it makes me think. Okay, so I learn, not that they transfer any knowledge to me, but by their question they have made me think in certain direction and stimulate my thought process. It may lead to something great. It has happened. So I learn from you as much as you learn, maybe not as much as you learn from me. But by asking questions and opening your mind and so on, you may make me think some things that I haven't thought before. Yeah. I can utilize. I didn't realize it's such a big hurdle over here for a foreigner to get a SIM card. Anyway.